Okay, welcome. Our main focus for chapter 24 is nuclear chemistry. What you need to know before we actually start this chapter is definitions of isotopes and subatomic particles. So you can go back to chapter 2 if you need a little refresher on that, but we're going to be using that terminology here in this chapter right from the beginning. Okay, so for section 24.1, our focus is radioactive decay and nuclear stability. So a stable nucleus remains intact indefinitely. So it's going to remain together. It's not going to fall apart. It's not going to disintegrate. This means that the vast majority of nuclei are unstable because over time they do degrade. So in case, again, you're kind of fuzzy on, what I mean by a nucleus, etc. So a nucleus, inside the nucleus of an atom, there are protons and there are neutrons, and then on the outside there are electrons. So when we're talking about the stability of a nucleus, we're talking about this area right here. This is our nucleus. So by definition, an unstable nucleus is radioactive. I don't know if you guys have seen the movie, I think it's Radioactive, right? That focuses on Marie Curie and her discovery of a couple of elements and radioactivity, etc. But it's a really fun movie to correlate with this topic. You can kind of see it in action. Okay, so what's the definition of radioactivity? Radioactivity. It is the spontaneous disintegration of a nucleus by the emission of radiation. So that means this is disrupted somehow, right? So the number of protons and neutrons together, they change, or something happens to where they go from a more unstable state to a more stable state. All right, before we get into what this looks like and fulfilling a couple of our objectives for chapter 24, let's look at how nuclear change is contrasted to chemical change. So far in class, we've really been focusing on chemical change, really for the whole semester. In most of chemistry, that's what we're focusing on, is chemical change. But this is a little bit different from nuclear change. So in chemical reactions, the focus is the electron. What's happening with the electrons? How are electrons being exchanged? How are they used to form bonds, etc.? But the focus for nuclear reactions are nucleons. So that's your protons and your neutrons. That's our focus. So what affects chemical changes? What affects chemical changes is temperature and pressure. But temperature and pressure do not affect nuclear reactions, so we don't take temperature and pressure into account when we're looking at radioactive decay or any type of nuclear change. Okay, so that's why you won't see that brought up in chapter 24. All right, so let's get familiar with some terms and notations before we go on to our next page. So terms that we're going to be using and notations that you should be familiar with are protons, neutrons, electrons, nuclide, and isotope. These are the terms we'll be using. Notation for the proton is this. Okay, you'll see a P plus like this. There's other ways, or you can fill in the blank if there's other notations that you're familiar with. There's other ways to represent a proton. Neutrons in 0, or, there's other different ways to represent neutrons. Electrons, this is usually what we're going to be using, but there's, of course, always other ways to represent an electron. What about nuclide and isotope? Those are relatively newer terms, at least to this. Well, nuclide is to this chapter. Isotope is a term from chapter 2, but we haven't discussed it that much. So nuclide is a nucleus with a specific number of 2 types of nucleons. So again, the nucleons are our protons and our neutrons. So a nuclide is any nucleus with a specific number of 2 types of nucleons. So we're looking at the number of protons and the number of neutrons. An isotope is very similar, but an isotope is an atom with a set number of protons, but different number of neutrons. So you will be familiar with the, carbon 12 and carbon 14. Both of these are carbon, which means they have 6 protons, But this number right here refers to their isotopic number, which means overall it has 14, carbon has 14 nucleons, and in this case, this isotope, carbon-12, has 12 total nucleons. So you will be seeing this type of notation a lot in chapter 24. Okay, when a nucleus does undergo decay, when a nuclide starts to disintegrate, it emits a type of radiation. So you should be familiar with 3 major types of radiation. The first type of radiation is alpha radiation. So let me zoom this in. The notation, the general notation for alpha radiation is your little alpha sign. The notation for beta is a beta sign, and then for gamma is a gamma symbol. So the Greek symbol for gamma. So the explanation of alpha is that it is the process in which a nuclide loses a helium-4 nuclei. We'll talk about that a little bit more below. For beta radiation, in the process of a nuclide emitting a beta particle, they are in essence losing a high-speed electron. And then gamma, in the process of a nuclide radiating gamma particles, they are losing high energy photons. We're going to use these notations to balance nuclear equations. And before we get into nuclear equations, I just want to remind you what certain symbols mean. We have the symbols A and the symbol Z that we're going to be using here and here. So let's talk about what those mean. So first, let me move my little Z just to give me a little bit more room. A is the total number of protons and neutrons. It's referred to as the mass number. Mass number. Z is the number of protons, and it is referred to as the atomic number because it tells you what type of atom it's referring to. Okay, so the central principle that we're going to utilize when we balance nuclear equations is that the total A and Z of the reactants equals the total A and Z of the products. So it's very similar to chemical equations when we are balancing both sides of the equations. That's the same thing we're doing here. We're just paying attention to the numbers of protons and neutrons specifically. All right, so before again we get into some balancing, let's look at more specifically the modes of radioactive decay. So we talked about types of radioactive decay. These are general categories, but now we're going to get into more specific what's happening to a nuclide when, let's say, an alpha particle or a beta particle is emitted. Okay, so in alpha decay, what's emitted is an alpha particle, so you'll see this. Another notation, though, it could look like this: alpha 2, 4, 2 plus, or you might also see a helium 2 plus, like that. Okay, so remember the number at the bottom is the number of protons, and the number at the top is your A, or your number of protons and neutrons together. So let me give you an example of something that undergoes the process of alpha radiation. So we have radium 226. Radium has an atomic number of 88. If it undergoes alpha decay, what's going to be left, or what's going to be emitted first, is an alpha particle and radon. Radon 222. And that has an atomic number of 86. Why is that? So if this loses an alpha particle, notice there are going to be 86 protons left over because the number of protons on the right has to equal the number of protons on the left. And in addition, the total number of nucleons, number of protons and neutrons on the right, has to equal the number of neutrons and protons on the left. So this is how you balance a nuclear equation. All right, so let's talk about what has been changed in this process. What has been changed is that the overall number for what's called the daughter nuclei, the daughter nuclide, this is my parent and this is my daughter, A has decreased by 4. Okay, notice it started at 226 and went down by 222, so A is decreased by 4. Z, my atomic number, has decreased by 2. So I started with 88, now I'm down to 86. And then specifically the number of neutrons has also decreased by 2. Decreased by 2 because these two together has to equal the overall number of nucleons that have been changed. All right, beta minus is a mode of beta decay. Beta minus is also referred to as negatron emission. All right, so you'll see that represented like this, like a beta minus, or you would see it like this, -1 and 0. All right, what's happening in beta minus? I'll put a little note right here. What's happening is that a neutron in the nucleus is being converted to a proton. So neutron is changing into a proton. You may also see it like this, a neutron. This is one of the other ways to write neutron and proton, is being converted to a proton. Therefore, a negatron or a beta minus particle is being emitted. All right, so this is the radioactive emission. This is the radioactive particle that's being emitted. An example of, let's do beta decay, might look something like this, an overall balanced nuclear reaction. Let's start with nickel, and that's 28 protons, 63 total nucleons, and it's decaying and it's losing a beta minus. So let's just think about this. Well, the right-hand side needs to equal the left-hand side, so that means I'm going to have the number 29 here at the bottom, which refers to copper, and I'm not changing the number of overall nucleons, so this is 63. All right, so 28 plus -1 equals 29 plus -1 equals 28. 63 plus 0 gives you 63. So what's the overall change in A? The overall change in A is 0. Okay, the top number for the daughter nuclide did not change. The number of Z, I've added 1 proton, so I'm +1 here. Then the overall change in the number of neutrons, I've lost 1 neutron, because again, these two numbers have to add together to give me 0. All right, so I keep using this term daughter nuclide, and I haven't even really talked about that in this lecture just yet. But if you want to make a little note to yourself, the daughter is what's being produced. So the parent is what you're starting with. The daughter nuclide is what's being reduced. So the daughter is always going to be more stable than its parent. Lord willing, that happens in life too. So this one on the right-hand side, whatever your nuclide is on the right-hand side, that's referred to as a daughter, and on the left, this is referred to as a parent nuclide. So let's get into positron emission. I'm just going to clear a little bit of space right here for myself because I kind of invaded the bottom territory. Okay, so for positron, you may see positron denoted beta plus, like this, with a beta and a plus, or you could also see it like this, beta 1 and 0. So in beta plus, or in positron emission, what's happening is a proton is being converted to a neutron. So what's happening is that a proton is turning into a neutron, and what's being emitted is a positron. A positron is the antimatter of an electron. I know, it sounds weird, right? Just the exact opposite. in charge, except it has the same mass and same other features as an electron, except that it is positively charged. It is not a proton, it is a positron. Okay, an example of a balanced reaction in which a nuclide disintegrates and emits a positron may look like this. Carbon, let me do it in black. So carbon 11 gives off a positron, which one of its protons converts into a neutron. And so what we have at the end is 5 total protons, but the same number of neutrons and the same number of neutrons plus protons, our mass number. So the overall change in A is still 0. However, our change in Z in this case is going to be -1. Our change in N is +1. Perfect. All right, so the third mode of beta decay is called electron capture. So in the process of an electron capture, an electron that is very close to the nucleus is being captured. It's being taken into the nucleus. So we may see this denoted like a little E, -1. So like that would be electron capture. And what's also being emitted in this process is X-ray, is an X-ray. That's what's being given off some high energy in the form of electromagnetic radiation. So what's happening in this process when an electron is captured is that a proton from the nucleus reacts with that electron and it creates a neutron. As you might suspect, a neutron is neutral, so if you put a proton and an electron together, it creates a neutral particle. So the only difference for a reaction like this is the electron capture is seen on the left-hand side of the equation. So it's a little bit different than what we've written so far. An example would be something like iron 55. So iron has 26 protons, total of 55 nucleons. We'll write the electron that's being captured. And so what we end up with is 25 protons. It changes the identity of the atom altogether, but doesn't change the overall mass number. And then there are some X-rays being emitted. And neutrinos, which we're not going to get into. Neutrinos. So this basically has the overall same net effect as a positron emission. So as the one right above it, right here, positron emission. Although it's a different process, right? A positron is being emitted here, whereas an electron is being captured in this case. In gamma emission, what's being emitted is gamma rays. And nothing changes in terms of the number of protons, neutrons, or overall mass number. So what really is happening is an excited nucleus is becoming stable by emitting some gamma rays. Okay, so usually you're not tested on that because there's not a lot to test you on, except for the fact that I could ask you, okay, in what type of radiation is there no overall net change in the number of nucleons? So that might be what I ask you about, but it's really just a process to stabilize the nucleus. And it can often couple different types or accompany different types of decay processes. So in the event of an alpha decay happening or beta decay, or even electron capture, there will be some gamma rays that are emitted. So it's usually not, and it doesn't happen necessarily often completely on its own. It usually accompanies some other type of decay process. Okay, so we're going to use this information to predict stability of certain nuclides. There are key patterns that we're going to use to determine whether a nuclide is stable or unstable. We're going to use first the number of neutrons to number of protons. We're going to look at the ratio of neutrons to protons. We're also going to look at the total mass of the nuclide. Okay, so total mass means the total mass number, the number of protons and neutrons together. That's what we're going to use to determine whether a nuclide is likely to be stable or not. So what we can take from that is when N is equal to Z, so when the ratio is close to 1:1, those are usually stable nuclides. And when N, or the number of neutrons, is much bigger, right here, than the number of protons, that's mostly unstable or radioactive. And the last key piece to keep in mind is that all atoms heavier than bismuth are radioactive. So what we can conclude here is that really heavy nuclides are unstable. All right, so stability is related to the structure of the nucleus. So how is the nucleus structured? How is it held together? That gives you an insight into how stable a nucleus is. So they're related in the following ways. First, the effect of the strong nuclear force. What's the strong nuclear force? So within a nucleus, again, you have little protons. We'll draw them as these little spheres, red spheres, and then you have little neutrons. Let's just say you have 3 of each. What holds those together? Well, it's not the charges per se, because protons are positively charged and neutrons are neutral. What holds them together is what's called the strong nuclear force, and this only works at when the nucleons are really close in proximity. But when they are really close, it's really effective to hold that nucleus in place. So that means when you have a smaller number of nucleons, you typically have a more stable nuclide because they're closer in proximity. Number 2, even number of nucleons generally have more nuclides that are stable. Again, why is that? So think of it, if I had a nucleus and what's holding the protons and neutrons together is the strong nuclear force. But let's say I have a bunch more neutrons than I do protons. Okay, notice there's no proton right between maybe these two that's really holding them together. There's not one between these two that's holding them together. So this is a less stable nucleus because there's not an even number of protons and neutrons to really balance and create a strong force that's holding the nucleus together. And lastly, this is a more abstract concept, that this is nucleon energy levels, kind of similar to when we're looking at electrons. When electrons are at certain spins, when they're opposite spins or the same spin, that affects their stability. That's the same basic idea for nucleons. Nucleons are thought to be in certain energy levels, and specific energy levels allow for a more stable nucleus. All right, how do we predict the mode of decay? We're going to use these 3 predictors to tell us what decay process a nuclide is most likely to undergo. First, neutron-rich nuclides will undergo beta decay or negatron emission. So this is going to be this type of emission. Proton-rich nuclides generally undergo positron decay. So this would be positron or electron capture, like that. And then heavy nuclides undergo alpha decay. And this is much easier to understand in our next slide. So let's look at this in format. This is referred to as the valley of stability. How this is laid out is on the x-axis, this is the number of protons a nuclide has, and this is the number of neutrons a nuclide has. And these little dots right here underline or underscore the type of nuclides that are stable, that are most likely to be stable. So notice this area, so anything that has a ratio that's over here, this is a nuclide that is more rich in protons as compared to the number of neutrons. So let's say you had, 80 protons and you had 40 neutrons. That would put you in this area right here, which means you're more likely to undergo positron emission or electron capture, which decreases the number of protons that is in that nuclide. So you're going to most likely undergo this. If you're really high in the number of neutrons, then you're more, then you're more likely, positron, sorry, I wrote this one a little wrong. Positron emission, this one, excuse me. So going back to beta decay and neutron emission, if you are very neutron rich, you're more likely to undergo negatron emission, which you're losing a neutron and it's converted into a proton. So that basically makes a more stable nucleus. And then anything that's super heavy, right, that has a ton of protons and neutrons, that's more likely to undergo alpha decay. So you're losing, in that case, let me do a different color. In that case, you're losing protons and you're losing neutrons. So that aids in stabilizing the nuclide. So let's use this in the next page to answer some questions. All right, so write balanced equations for the following nuclear reactions. So I want you to pause the video and then attempt A, B, and C, and then resume the video when you're ready to see the answers. All right, for example, question 1, part A, we have thorium-232, which means we have a total number of 232 nucleons. Thorium has 90, according to the periodic table, 90 protons. When it undergoes alpha emission, it's losing an alpha particle. And then what's resulting is 88 protons, because 88 plus 2 gives you 90. And then it has 228 nucleons. 228 plus 4 gives 232. The 88 tells you that this is the element radium. All right, same thing with B, except electron capture. We have zirconium 86. Zirconium 86 has 40 protons according to the periodic table. It captures an electron, which yields yttrium that has 39 protons, because 40 minus 1 gives 39. There's no change in the number of nucleons, so it has a total number of 86 nucleons. And then last part C, positron emission by N12. Nitrogen has, not 5. Nitrogen has, it's always good to double check these, has 7 protons. So this is going to change the identity of our last element. So it has 7 protons. When it loses a positron, that means that my resulting daughter nuclide has to have 6. So 6 protons makes it the element carbon. The number of nucleons total does not change, so I end up with 12 at the very end. All right, let's go on to example question 2. Which nuclides would you predict to be stable and why? What you're going to do is use the value of stability chart. You first need to identify the number of protons and the number of neutrons for both of these, and then see where they line up on the valley of stability. So go ahead and pause the video now and then come back. All right, let's start with our iodine. 127. So the number of protons that iodine has is 53, which means the number of neutrons is 127 minus 53. So that gives us 74 neutrons. 127, yeah. Let's do the same for 10. So 10 has, let's see, on the periodic table has 50 protons. That means the number of neutrons is 106 minus 50, which gives us 56. And then for astatine, oh no, this is arsenic, excuse me. For arsenic, it has 33 protons. So the number of neutrons is 68 minus 33, which gives us 35. 68, 106, 127. Great. So what we're looking at on the value of stability is this ratio. All right, so let's first look at 53 protons and 74 neutrons. What do we end up getting? Okay, so looking at the value of stability, the number of protons being 53 would be right here. Let's do it with a little blue dot. And then the number of neutrons would be right here. So where they meet up is somewhere right here. Notice that's in the valley of stability. So if these overlap in the valley of stability, right here and right here, that means that I-127 is stable. All right, let's check the next one, 10-106. So 50 and 56, let's find where that is in on the valley of stability chart. So 50 is right here, and then 56 is right here. So they meet up about right there. So that looks rather like it's pretty much in the valley of stability, so we're going to say that's stable as well. And then let's do our last one, our arsenic 68. So that has 33 protons, and it has 35 neutrons. So that's pretty stable. If it's going to go under any emission, it would be positron emission or electron capture. We're going to say it's relatively stable as well. All right, that's it for today.